this mistake just now. I accidentally hit the power button instead of the escape button on my computer, so it's restarting. So it's going to take, it's going to take a few minutes. But that doesn't mean we can't continue while it's getting its brain back together. Let's look at the first slide, not the first slide, well, the first slide on your handout. Anatomy concepts. Let's do this. We don't need the slide, we don't need the projector for this. Everybody stand up. Use your index finger, point to the most superior or most rostral part of your body. Superior. Above. Rostral is referring to head. Point to, you don't have to bend over, point to the most inferior or caudal part of your body. Inferior means below, caudal means tail, but we don't have tails, but it doesn't, this is not your caudal part of your body. Use your hand to indicate your anterior or ventral surface. This is anterior ventral. So use your hand similarly to point to your posterior or dorsal. Posterior, dorsal. Medial. In the middle. Toward medial means towards the middle or at the middle, midline. Lateral. Out there somewhere. Lateral. Proximal. Proximal. So point to the part, use your right hand to point to the part of your left arm that is proximal. If proximal, like proximity, means near. The near we're talking about is near to the midline. So this is the part of your arm that is proximal. So what's the part of your arm that is distal? Distal, proximal. Proximal, distal. Anterior, posterior. It's a language. You're going to learn this language. Use your right forefinger to point to your ipsilateral eye. Your right forefinger to point to your ipsilateral eye. Your right eye is ipsilateral to your right finger. Ipsilateral means same side as. So use your right forefinger to point to your contralateral eye. Right? So ipsilateral to my right, contralateral to my right. Ipsilateral to my left, contralateral to my left. Flex both of your arms. Flexing the forearm. Okay? So flexion and extension of the elbow. Flexion and extension of the elbow. Flex your shoulder. Flexion and extension of the shoulder. What Hannah did is abduction and adduction. So none of this makes perfect sense. Flexion, extension, abduction, adduction. So you can, well, abduction, adduction. We're using gravity to do adduction, but there are muscles that do adduction too. We'll talk about, you'll learn which muscles are doing abduction and which muscles are doing adduction, which muscles are doing flexion and which muscles are doing extension. So flex, you can't do both of these at the same time. Flex one of your knees. Flexion and extension of the knee. Flex one hip. Flex your leg at the hip, but only do one of them because the other one won't take. Flexion and extension. No, so this is abduction, and this is adduction of the hip. This is flexion, and this is extension of the hip. So the hip and the shoulders can do multiple movements, including rotations that we're not going to focus on. We're going to focus on flexion, extension, abduction, adduction. Flexion, extension, abduction, adduction. Flexion, extension. You can't abduct or adduct your elbow, not without breaking. Flex your fingers. Extend your fingers. The anatomically neutral position is like this. Now you'd say, well, that's weird. That doesn't feel neutral. If I sort of don't move anything, my hand goes like this. That is not the anatomically neutral position. The anatomically neutral position is like this. So it doesn't, you have to use some muscles to get into the anatomically neutral position. Supination, pronation. We'll use that occasionally. Supination, pronation. We do that mostly in our arms. We don't do that in our legs very much. Some of you may have heard of pronated ankles. That's pronation of the ankles. Supination of the ankles. We don't do that a whole lot. Oh, here's one. So I can't see if you do this, but flex your toes. Flexing and extending your toes. Right? You can flex and you can extend your toes. Flex one of your ankles. So I am now flexing my hip and flexing my ankle. It's called dorsiflexion, but it's also flexion. I am now doing extension of my ankles, which is called plantar flexion. So this is nasty language. Anatomists are not your best friends. They're going to use some language that sometimes makes sense and sometimes doesn't make sense. This is flexion of the ankles. Heel walking is flexion. Toe walking, tippy toes, is extension of your ankles. We're going to learn about the muscles that do that. Okay, I think my computer is back to life. You can sit down. All right, I think we're done with the anatomy. Okay, so we're going to skip this slide because this is just where we're going, but we've already been there. Right. We're going to talk, we did some anatomy, lingo, language. You're going to be learning the language of anatomy, the muscles that do these things, and the names of the things that they do, extension, flexion, abduction, adduction, etc. It's a language. It's got verbs and nouns. Verbs like flex or extend, nouns like the biceps brachii flexes the elbow. The language that you're going to learn. Questions about some of the anatomy language before I move on. On the slide, it talks about origins and insertions that I'm not going to ask you to learn. But, you know, a muscle has an origin where it connects to one bone and an insertion, typically where it connects to another bone to allow the movement. A hardcore anatomist would be expecting you to learn the name of the muscle, the action of the muscle, its origin, and its insertion, what bones it connects to. We're going to trim that a little bit. I'm going to expect you to know the names of muscles and what they do, but not origins and insertions. Oh, I didn't do sagittal. Different, so we're a three-dimensional entity, right? And we have names in 3 dimensions. Sagittal is a plane that runs like this. So this is a midline or a medial sagittal plane. This is sagittal, coronal. This is the coronal plane. And typically we only use that in the head. Sagittal, coronal, transverse, or horizontal. So we could talk about a horizontal section through the abdomen, or a horizontal plane in the head. Sagittal, midline sagittal, lateral sagittal, right lateral sagittal. Anterior coronal, posterior coronal. Okay? So now we're going to turn our attention to binding. So some of that was new, new anatomy maybe for many of you. This is review and embellishment from cell phys again. You'll remember we need to talk about binding. We've talked about binding already. Ions bind to their transporters. Ions bind to their channels. Neurotransmitters bind to their receptors. Neurotransmitters bind to the proteins that pump them back up, the serotonin reuptake protein, etc. So we need to talk about some of the formalism of binding. Ligand and a receptor bind. It's reversible. All the binding reactions that we're going to talk about are reversible. You've got to remember reversibility. The cartoons might only show you one thing. They might only show you binding, or they might only show you unbinding. But you have to remember that it's an equilibrium, and there's binding and unbinding all the time. And it's very fast, milliseconds. Thousands of times per second, things are binding and unbinding. You learned in cell phys the equation for the association constant of a binding reaction. I'm not going to ask you to remember that. we can draw this reaction as a binding reaction going from left to right, or as an unbinding reaction going from left to right. We can do it either way. This is showing association going from left to right, and this is showing dissociation going from left to right. And we can also write a dissociation constant, the same concept as an association constant. In this course, we are mostly going to be focusing on dissociation constants. If we take the algebra, which I am not going to go through, and we take the idea that the amount of ligand that is bound can be turned into a variable called the amount bound. The amount bound is a function of the maximum amount that can be bound. Well, what's the maximum amount that can be bound? It's the concentration of receptor. But we want to put the receptor aside and just call it the maximum amount that can be bound. But that is a factor that is due to the number of receptors. Low number of receptors, low B max, the maximum amount that can be bound. High number of receptors, high B max. Typically, we normalize this to just whatever the receptor is. B max divided by, again, I'm just giving you the equation with a little bit of homework. I could derive it for you, but I can't without doing my homework, so I'm not going to do it. Here is the denominator. So let's just see if this makes sense. If the ligand concentration is very high, no, let's start low. If the ligand concentration is very low, then this fraction becomes a big number, right? Because it's got a small denominator. This is a big number. Kd is a constant, right? So if the ligand concentration is small relative to the Kd, which is determined by the reaction, low number here, some number here, this fraction becomes a big number. This denominator becomes a big number. This fraction becomes a small number. Small amount bound. That makes sense. Small amount of ligand, small amount bound. Okay, just making this equation make sense so that I didn't just throw it at you and expect you to get it. If the ligand concentration is high, this number becomes small, right? This denominator gets close to 1 because this is a small number, small, 0.001 or whatever. This denominator becomes close to 1. This number becomes close to Bmax. So when the ligand concentration is high relative to its Kd, the amount bound is getting close to the maximum. That makes sense. High concentration of ligand, high amount bound. Reaching a maximum. Can't just keep going up and up and up because we have a certain number of sites. So let's turn that into the binding curve. This is going back to self-is. All this, I know these concepts were not fun then, but we need to use them now again. Low concentration of ligand, low amount bound. High concentration of ligand, some value close to Vmax. Okay, so far so good. Let's look at what happens when the ligand concentration is equal to Kd. Ligand concentration is equal to Kd, whatever the Kd is for this binding reaction. Remember, every reaction has its own Kd. Well, if this is equal, this is 1. If this is 1, this is 2. Vmax over 2. So 1/2. So somewhere on this is a point where the amount bound is 1/2 Vmax. Where is that point on this curve? I mean on this axis? This is the Kd. Because I said, when the ligand concentration is equal to the Kd, the amount bound is 1/2 Vmax. And if you plot this equation, we now have 3 points on this equation, but if we plot this equation, we get a rectangular hyperbola. That's, I can do better than that. Draw a rectangular, just a hyperbola, through the points. There, that looks better. So there are data points. So if we had this concentration of ligand, we would get this amount bound. And if we had this concentration of ligand, we would have this amount bound. This is a graphic representation of this equation. Now let's talk about what happens if the same ligand binds to a receptor that has a lower Kd. Same ligand, different receptor, lower Kd. So let's just say the ligand binding to the red receptor binds with a Kd, say here. So Kd 2. Or prime, or whatever. It's binding to a different receptor, the red receptor. You've got a point here, right? If there's no ligand bound, if there's no ligand, there's no ligand binding. We'll just say that the red receptor has the same Vmax, same number of receptors. What is different, though, if this is the Kd? If this is the Kd, then the half maximum, then it reaches half maximal binding here, not here. Right? And so we could draw a curve. Remember, it's the same ligand binding to a receptor with a lower Kd. And so we would draw a curve that goes through that half point, starts at 0, goes through that half point, and then approaches the same Vmax. Same ligand binding to a different receptor. Which receptor has the higher affinity for the ligand? The red receptor or the blue receptor? Somebody say an answer. Red or blue? Red. Red has higher affinity. And here's the key concept. Lower Kd, higher affinity. That's a key concept. Lower affinity, higher affinity. More is bound, at a given concentration to the red receptor than to the blue receptor. Okay, so you should have on your page a curve that looks something like this. Okay? High affinity, low affinity. Ligand concentration, amount of ligand bound. This is talking about an enzyme that has a Km. I am going to mostly be talking about binding, which is not necessarily an enzyme. It's not doing an enzymatic reaction. It's binding, and so we talk about Kd. So when we talk about binding, rather than enzyme activity, we talk about a Kd, not a Km. But lower Kd, higher affinity. Higher Kd, lower affinity. Substrate is just another name for ligand. Substrate is the enzymology term for a ligand. So you'll see, you can see, I just pulled this up off the internet, and I didn't change everything about it. The concepts are the same. The equation is the same, except that in enzymology, it's Km here, not Kd. Questions about binding Kd, Km, Bmax, bound, etc. That was reviewed. Now we need to talk about something new. Inhibition. Competitive and non-competitive inhibition of receptors. So again, this is a cartoon from the internet, and it's talking about an enzyme that does some catalysis. Well, we're just talking about a receptor. So enzyme here is a receptor. And most of our receptors are in the membrane, so you just have to imagine this is a receptor in a membrane. Here is the ligand. Here is a competitive inhibitor. Everything is reversible. The binding of the inhibitor, binding and unbinding. Binding of the substrate. If the inhibitor is not present or is unbound, then the ligand can bind. And if the ligand unbinds, then the competitive inhibitor can bind. Right? So it's a competitive binding reaction. But all we're seeing, this snapshot is when the inhibitor is bound and the ligand is not. But we could just as easily have cartooned this when the ligand was bound and the inhibitor was not bound, because they're competing and they're in equilibrium. And we're just seeing one snapshot of what's going on. Okay? So think about binding and unbinding. And when the receptor is vacant, one or the other of those two molecules can bind. What is the difference between a ligand that binds to a receptor and an inhibitor that binds to a receptor? They're binding at the same site. What's the difference? Hannah?
For a substrate, the enzyme will, follow it to break it down, whereas an inhibitor is just there to block the substrate from binding to the enzyme.
Exactly. When the ligand binds to a receptor, the receptor is activated. If it's an enzyme, it's activated to do its enzymology. If it's a receptor, it's just activated to do its receptorology. When a ligand binds to a receptor, it becomes activated. And when a competitive inhibitor, this is a competitive inhibitor, when a competitive inhibitor binds, but it doesn't cause the receptor to activate. So all it does is squat on the binding site and prevent the ligand from binding. Another name for this ligand is agonist. An agonist is a ligand that activates a receptor, and an antagonist is an inhibitor. Well, it's a ligand that does not activate the receptor, and in this case, this is a competitive inhibitor or a competitive antagonist. There again, learning the language. That is competitive inhibition. There are other types of inhibitors. So here is the receptor. Here is the agonist. Here is a different kind of antagonist or a different kind of inhibitor. It binds to a different site. They are called allosteric inhibitors. So competitive inhibitors, non-competitive or allosteric inhibitors. Allosteric means just different place. So let's look at what happens. When the allosteric inhibitor binds, it causes a conformational change of the enzyme that renders the binding site non-functional. It's also in equilibrium. We are seeing a snapshot of when this receptor is occupied by the allosteric non-competitive inhibitor. But when it's unbound, the receptor undergoes a conformational change that reactivates, that refunctionalizes the binding site. So we're going to see in the next slide, a competitive inhibitor does not change the maximum amount of ligand that can be bound, because if we have a huge concentration of ligand, it can outcompete the inhibitor. Right? They're competitive. If a non-competitive inhibitor is bound, it's as if we are taking a fraction of the receptors out of the picture. Some fraction of the time, the receptor is occupied by the inhibitor that renders the binding site invisible to the ligand. Some fraction of the time that depends on the binding of the allosteric inhibitor. If we have a high concentration of allosteric inhibitor, this receptor is, for all practical purposes, gone, because the receptor is always occupied by an inhibitor. But if the inhibitor is not huge in concentration, remember, sometimes it's unbound, and so sometimes the ligand can bind. Let's see how this looks on our curve.
Bob?
Yeah.
I have another question.
Yeah.
So for the substrate, or for the competitive inhibition, and also the allosteric inhibition, you said that there are times when the substrate will be bound, and times when the inhibitor will be bound, and times when neither will be bound. Essentially, it's kind of select any random amount of time when you have ligand present and you have inhibitor bound, and one or of the two could be bound. Is there a way of telling the chances of how often a ligand or a substrate will be bound or an inhibitor will be bound, and is that controlled?
It's controlled. Could you hear the question back there?
No, I couldn't.
The question is, it seems random, the binding of the inhibitor or the binding of the ligand, but it can't be random because there's some control there. What is controlled is the concentration of the ligand or the inhibitor relative to its KD. If the ligand concentration is high relative to its KD, it's going to tend to be bound. If the inhibitor concentration is high relative to its KD, it's a different binding reaction because it's a different molecule, then it's going to tend to be bound. The competition is related to the relative KDs of those two ligands, the substrate or the agonist and the antagonist.
So if you wanted one to be bound more or less, you would change the concentration of the ligand or inhibitor?
So if you are an experimentalist and you have control, yes. If you are a cell, you release more of the ligand, or you mutate, you evolve a receptor that has a very high affinity for that ligand.
Oh,
Remember, we have evolution going on here in the background.
gotcha. Thanks.
Okay. Okay, so let's talk about a receptor that has, the receptor has a Vmax. The ligand that we're going to talk about is the agonist. The agonist concentration. So in the absence, let's just put up the control. No inhibitors. No inhibitors. Well, we start here, we end here. We've got a half. We've got some KD for the binding of the agonist. So then at the KD, we got 1/2. So we have a rectangular hyperbola, the name of the mathematical function, something like that. No inhibitor. Now let's add a competitive inhibitor. Red is going to be the same receptor, the same agonist concentration, and we have some concentration, not a huge concentration, but some concentration of the inhibitor. There are some points that are the same and some points that are different. Do we have a point here at the origin? Yeah. If we have no agonist bound, if we have no agonist, we have no binding of agonist, even though we have an inhibitor. If we have a competitive inhibitor, what other point is the same on this curve? Bmax. If we have a competitive inhibitor at some concentration, but we have an agonist concentration that is so high that it is dominating, no matter how much of this we have, it's going to go to the same Bmax. But it's an inhibitor. So it's not going to follow the same curve. At this concentration of ligand, less is going to be bound if it's competing with the competitive inhibitor. And at this concentration of ligand, less is going to be bound, right? I'm just showing you that, yeah, I still believe it's an inhibitor. Well, what am I doing here? I'm drawing a rectangular hyperbola that looks like that. Same origin, same point way out there, forget the wiggle. When we have a very high concentration of agonist, but it's an inhibitor, so it's lower. What has changed? The concentration of agonist that gives us, in the presence of the inhibitor, that gives us an apparent half maximal binding, because there's competition, is a higher concentration. So this is the Kd apparent of the agonist in the presence of a competitive inhibitor. Bottom line, a competitive inhibitor increases the Kd, increases the apparent Kd, decreases the apparent affinity of the receptor for its agonist. Now let's do questions about the competitive inhibitor. Now let's do a non-competitive inhibitor. Some of the points are the same and some of the points are not the same. I've got a non-competitive allosteric inhibitor. Same agonist, same receptor, with a non-competitive allosteric inhibitor. What's the same? Well, if I have no agonist, I have no bond. If I have a huge concentration of agonist, but I have some non-competitive antagonist, do I have the same Vmax? I don't. Because some of the time, let's go over here, some of the time, the receptor is occupied by the allosteric antagonist and is out of commission. Some of the time. So it's like the number of sites is decreased, because some of the time there is no site available. So we have a different Vmax. If we have a moderate concentration of inhibitor, we have a lower apparent Vmax. What is the same? So we have a same origin, a lower apparent Vmax, because some of the time the receptor is out of commission. What's the same? The Kd. Because when the receptor is in commission, it's the same old receptor. So we have the same Vmax, we have the same half maximal, but remember, it's relative to this half max, this max, so this is the apparent half Vmax with the non-competitive inhibitor. So there's a point here, so things are looking on top of each other. Oh, we get a curve that looks something like that. Unfortunately, I drew it where they're both on top of each other. But here is a way. Here is a way to see it. No inhibitor. Some Kd. With a competitive inhibitor, the apparent Kd is higher. The Bmax is the same. Same Bmax, higher KD. With a non-competitive inhibitor, lower Phi max, same KD. That's the key concepts for competitive and non-competitive inhibition. If you take biochemistry, you'll learn about other ways to graph these functions. But that's what we're going to do today. So, what's coming up next is some clickers. And I'm going to assign these as homework. So those of you who have seen me do this before, you already know what I'm doing. I'm paying attention to the clock. I'm saying there's some things that you're going to learn at home, and then you're going to ask your friends, or you're going to ask me if you don't understand something. I will post the answers, but not today, because I want to give you a day to do the work, because you coming up with the answer is important for learning. And then I will post the answer, and then you can look at your answers against mine and say, oh yeah, what was I thinking? Or if you're saying, wait a second, I don't get that, I better ask Bob, you send me an email. There is a small but non-zero chance that I'm wrong. So don't assume that I'm always right. There's a not small chance that the way you're thinking of it and the way I'm thinking of it are not exact. You're not wrong, we're just not communicating well. There is a chance of that. And that's when you ask me a question as well. Wait a second, I thought you said da-da-da-da-da. And I say, yeah, you're right in that situation, but this is the situation I'm talking about now. Or something like that. So there's a chance that you're right, and there's also a chance that we're just not talking the same language for that problem. Okay? So don't hesitate to ask me a question. Or Brittany, or a Peter. So I'm going to skip. So here's a pair of clickers. You're going to do these as homework. They're on, I printed them out for you, so you have them in front of you. The answers will be on Moodle tomorrow or Wednesday. Work on them as homework. Remember, your homework assignment, for today anyway, is to review these concepts, read the book, do the coloring book assignment, redo your notes, do what it takes to put this information into your head, into your brain. So I just skipped through the answers so you couldn't see them. Let's talk about receptors as molecules, not as concepts. Here's an image from your textbook. Here is a ligand-activated ion channel. A ligand-activated ion channel is a kind of receptor. Here is a G protein coupled receptor. You've seen this in cell phase. There are tyrosine kinase receptors. There are other kinds of receptor molecules that are coupled to enzymes that we are not going to talk about in this course. I don't want to say they're not important. They're extremely important. But these are the types of receptors we're going to talk about in this course. Ligand-gated ion channels and G protein coupled receptors. Ligand-coupled ion channels. Ligand binding, conformational change, ion flow. You're going to be working with some of these on the problem set. So I'm just going to move on. Here's a, remember it's not a blob. It's a protein with transmembrane alpha helices and beta sheets and subunits, usually colored, to give you in a sense of a subunit composition. So this is a glutamate receptor. Glutamate, a ligand-activated ion channel that is activated by glutamate, which is the most important excitatory neurotransmitter in your brain. your, your senior neuroscience majors who are working on their comprehensive exams are answering a question related to these receptors. This is one class of receptor. Here is another class of receptor, G protein coupled receptors. I hate this picture, even though it's from your textbook, which I don't hate, because the receptor is huge and the G protein is tiny, which is not right. Here's the way it actually looks. Here's the receptor, and here's the G protein. The G protein is every bit as big, maybe bigger, than the receptor. Nevertheless, this is the cartoon we have. The G protein, we're going to go through this for a few minutes. The G protein activates a second messenger generator. We're going to talk about a second messenger that might activate a kinase cascade or something inside the receiving cell. You've had this, all of you have had this, either in AMP, the other AMP, or in cell-phase. So I can go fast through this. Receptor with G protein. The red is the alpha subunit of the G protein. The orange is hard to tell. This is beta gamma. This is the beta gamma complex. This is the alpha subunit. This is the receptor. Here is a cartoon that I don't hate from your cell phys textbook. I like it better because it shows the receptor. What do I like about this? It shows the receptor. Why is it showing it as this snake in the memory? All of these receptors have 7 transmembrane alpha helices. It is one of the few alls I can say. So they are accurately cartooned as a protein with 7 transmembrane alpha helices. If you see a cartoon of a molecule in a membrane with 7 squiggles in it, they're talking about a G protein coupled receptor. If they're not, they're being really, really cruel. Because that's what we call a receptor. Receptor, G protein. The G protein alpha and gamma subunits are lipid linked. You learned about this in cell phys, I think. Anyway, you're going to do this as homework too. I want you to tell the story that is illustrated by these pictures. What do I mean? Here's the starting point. Okay? Let's start here. What is this? What words would you use to describe this arrow? I heard it. Binding is one. What's the other word? Begins with a D. You know it. Diffusion. The molecule is diffusing. It's not being sucked into the receptor. There's no vacuum here. It's diffusing, and then it finds, by luck, spontaneous, a binding site, and it binds. Diffusion and binding. What is cartooned in these red blasty things? What happens after binding? Conformational change. So, I want to talk through it, but I don't want to talk through it. I want you to do this as homework. Talk through the steps. Write out the steps. First one is diffusion and binding. Second one is conformational change. use your self-phys level knowledge to describe the rest of this story. It's part of your homework. Again, the answer will be on Moodle tomorrow or Wednesday. Ask me questions. There are 3 types of G proteins that we need to talk about. GS, S as in stimulatory, G, which you heard about in self-phys. I know that you did because I asked Lindsay. Or I taught you. GI, which is different, and GQ, which you didn't learn about in self-phys, but some of you learned about in AMP2. I'm going to ask you so this story is the same for GS, GI, and GQ. Up to this point, it's the same. In your problem set, I'm going to ask you to tell me the GQ story. But I think it might be good for you to review what is in, and convert it to words, what is in this story. What's happening here? What's happening here? What is this arrow? Write those words out. Tell the story that is embedded in this slide. If I wasn't running out of time, we would do this together. But I think you can do this at home. Okay, so I'm going to skip the next slide. I'm going to skip that one too because that's homework. Here is the slide that describes the GQ story. It's in your book. It's on the internet galore. One of your problem set questions is to describe this story. So here it is in cartoon, but again, binding, conformational change, da-da-da-da-da. Do that in your problem set. I forget which question it is, but it's there. And then there's a question about turning off. If you just turn on a receptor and you have no way of turning it off, you got a problem. You've either got cancer, or you've got epilepsy, or you've got some problem. All the receptors we're going to be talking about is they're turned on and then they turn off. We'll start on Wednesday with turning off. And then we'll move on to more neuroscience on Wednesday. Okay? So I didn't cover everything that I wanted to cover, but I covered most of what I wanted to cover. And I've given you homework assignments to cover what I didn't explicitly cover. But your textbook, your friends, your TA, me are available to help you learn outside of this room. Okay, so we're off and running. I hope you're not feeling too overwhelmed yet. I know that this is a challenge. I do understand that this is a challenge. But this is our challenge, and we'll do this together.